For centuries, the night sky gave us a powerful illusion that the universe is calm, balanced, and still. The stars appear fixed. The Milky Way stretches quietly across the darkness. Even as we learned that the universe is expanding, that expansion seemed smooth and uniform, carrying galaxies away from one another in every direction. But precise measurements of the cosmic microwave background, the faint radiation left over from the Big Bang, revealed something unexpected. Our galaxy is not simply expanding with the universe. It is moving. The Milky Way, along with our neighbouring galaxies in the local group, is travelling at roughly 600 kilometers per second relative to this ancient cosmic light. That motion has a direction, and when astronomers traced that direction across the sky, it pointed toward a hidden region, obscured by the dense disk of our own galaxy. They named it the Great Attractor. It is not a single object, but a vast region of enhanced mass concentration, powerful enough to influence the motion of entire galaxy clusters across hundreds of millions of light years. What lies there? How was it discovered if we cannot see it directly? And what does this motion reveal about the large-scale structure of the universe? To answer those questions, we must first understand how we learned that our galaxy is not standing still but falling through space. In order to understand why our galaxy is moving, we have to look much farther back, nearly 14 billion years into the past. Shortly after the Big Bang, the universe was a hot, dense plasma of charged particles and radiation. Light could not travel freely. It scattered constantly, trapped in a fog of electrons and protons. But as the universe expanded and cooled about 380,000 years after its beginning atoms formed, the fog lifted. Radiation was finally able to move unimpeded across space. That ancient light still fills the universe today. We detect it as the cosmic microwave background, or CMB, a nearly uniform glow coming from every direction in the sky. Its temperature is astonishingly consistent, just a few degrees above absolute zero. If the universe were perfectly uniform, that radiation would look identical in all directions. But it does not. When scientists mapped the CMB with high-precision satellites such as COBE-W MAP and Planck, they discovered a subtle temperature difference across the sky. In one direction, the radiation appears slightly warmer. In the opposite direction, slightly cooler. This pattern is called a dipole anisotropy. The simplest explanation is motion. If we are moving through this ancient radiation field, light in the direction we are travelling becomes blue-shifted, slightly hotter. Light behind us becomes red-shifted, slightly cooler. By measuring this temperature difference, astronomers calculated our velocity relative to the early universe itself. The result was striking. The Milky Way, together with a local group, is travelling at approximately 600 kilometers per second. This motion cannot be explained by cosmic expansion alone. Expansion moves galaxies apart uniformly. It does not create a preferred direction. Something is pulling on us, and that realization marked the beginning of the search for the Great Attractor. Once astronomers knew we were moving, the next question was obvious. Toward what? Velocity is not just speed, it has direction. And the dipole pattern in the cosmic microwave background provided exactly that, a cosmic arrow pointing across the sky. When researchers plotted this direction in galactic coordinates, it did not align with any familiar landmark. It did not point toward the center of the Milky Way. It did not correspond neatly to a nearby cluster. Instead, it aimed toward a region in the constellations of Centaurus and Norma, an area heavily obscured by the dense plane of our own galaxy. This presented a serious observational challenge. The Milky Way is filled with stars, gas, and interstellar dust. When we look outward along its disk, that material blocks visible light from distant galaxies behind it. Astronomers call this region the zone of avoidance. Not because nothing exists there, but because for decades we could not see through it clearly enough to map what lay beyond. And yet the motion persisted. Galaxy after galaxy, when measured carefully, showed similar peculiar velocities. Slight deviations from uniform expansion, all trending toward the same hidden direction. It was as if multiple rivers of galaxies were flowing toward a gravitational valley concealed behind a curtain of dust. By the late 20th century, enough independent measurements had converged to suggest that this was not random. There was structure there, something massive enough to influence motion across tens of millions of light years. Astronomers gave that region a name, the Great Attractor, but naming it did not solve it. If this gravitational basin was real, it had to be composed of enormous amounts of mass. The question now shifted from motion to matter. What exactly was hiding behind the Milky Way? If visible light could not reveal what lay behind the Milky Way, astronomers needed different tools. Interstellar dust is highly effective at blocking optical wavelengths, but it's far less opaque to infrared and radio waves. By shifting their observations into these longer wavelengths, researchers began to peel back the curtain of the zone of avoidance. Infrared surveys in the 1980s and 90s, including data from the Infrared Astronomical Satellite, uncovered thousands of previously hidden galaxies. Many of them were not small or isolated systems, but members of substantial clusters. Radio observations targeting neutral hydrogen gas added even more detailed tracing spiral galaxies, whose emission could penetrate the dust. Slowly a picture emerged. Behind the obscuring band of our galaxy lay a concentration of galaxy clusters centered near the Norma cluster, also catalogued as Abell 3627. X-ray telescopes revealed vast reservoirs of superheated gas trapped within its gravitational field, a clear signature of immense mass. The temperature of that gas, tens of millions of degrees, allowed astronomers to estimate how much matter was holding it in place. The numbers were impressive. The Norma cluster alone contains mass equivalent to hundreds of trillions of suns. It is one of the most massive nearby clusters in our cosmic neighborhood. Yet even this was not enough. When researchers calculated how much gravitational pull would be required to account for the full velocity of the local group, the visible mass in Norma and its neighboring clusters fell short. They contributed significantly but not completely. The gravitational valley seemed broader than a single cluster. The Great Attractor was not one mountain of mass. It was a landscape. And as mapping techniques improved, astronomers began to suspect that this landscape extended even farther than they had first imagined. As distance measurements improved, astronomers began looking not just at individual clusters, but at the motion of galaxies across vast regions of space. Instead of isolated velocities, they examined patterns, large-scale flows embedded within cosmic expansion. What they found was striking. Galaxies were not moving randomly. Across hundreds of millions of light-years, entire groups appeared to share coherent motion, drifting together toward the same general direction. This was not the pull of a single nearby structure. It resembled a gravitational current operating on a far larger scale. Then came a breakthrough in how cosmic structure itself was defined. In 2014, a team of astronomers introduced a new way of mapping our region of the universe using velocity flow lines rather than just galaxy positions. Instead of asking, "Where are the galaxies?" they asked, "Where are they going?" The result was a new cosmic address. We live inside a vast supercluster named Laniakea, a Hawaiian word meaning immense heaven. It spans roughly 500 million light-years and contains over 100,000 galaxies, all connected by shared gravitational motion. The Milky Way is not central within it. We occupy a minor filament along its outskirts. And at the heart of Laniakea lies a gravitational basin, the region traditionally associated with the Great Attractor. But even this was not the full story. Beyond Laniakea, farther still along the direction of our motion, lies an even larger concentration of mass, the Shapley supercluster. It contains dozens of massive clusters packed into a dense region of space, making it one of the most significant gravitational structures in the nearby universe. Suddenly the picture shifted. Perhaps the Great Attractor was not a single dominant force. Perhaps it was part of a chain of structure-nested gravitational wells extending across hundreds of millions of light-years. Our galaxy was not being pulled by a monster hidden in the dark. It was flowing along the contours of the cosmic web itself. It is tempting to imagine gravity as something active, a pull, a tug, a force reaching across space. But on cosmic scales, it behaves less like a hand and more like a landscape, mass-shaped space-time, where matter gathers space curves, and where space curves motion follows. When astronomers mapped the velocity field of Laniakea, they were not tracking isolated galaxies falling toward a single object. They were charting how entire regions of space are shaped by uneven mass distribution. The flow resembles water moving downhill, not because water chooses a direction, but because the terrain guides it. In this view, the Great Attractor is not a target. It is a basin in a vast gravitational topography, but something else complicated the picture. In 2017, researchers analysing velocity data identified an unexpected feature on the opposite side of our motion, a region of extremely low density. They called it the dipole repeller. It is not pushing us in any literal sense. There is no repulsive gravitational force at work. Instead, the absence of mass creates its own effect. If dense regions curve space inward, vast empty voids allow space to curve less. The imbalance contributes to the net motion we observe. Our galaxy's journey then is shaped by two factors: attraction toward dense regions like Shapley and relative motion, away from enormous underdense voids. We are not being pulled by a single structure. We are sliding through a gravitational gradient shaped by the largest structures in the observable universe. And this raises a deeper question. If gravity sculpts this immense cosmic web, if clusters, filaments, and voids define the flow of galaxies, then what invisible ingredient allowed such structure to form in the first place? If we could see only the luminous matter in the universe, stars, gas, and glowing clusters, the cosmic web would appear far too delicate to produce the motions we measure. The gravitational influence required to guide entire superclusters cannot be accounted for by visible matter alone. This discrepancy was not first discovered in large-scale flows. It appeared much closer to home. In the 1970s, astronomers studying spiral galaxies found that stars orbiting far from galactic centers were moving too quickly. Based on visible mass, they should have drifted away. Instead, they remained bound as if embedded in an unseen gravitational scaffold. The same principle applies on larger scales. Galaxy clusters contain vast amounts of hot gas visible in X-ray wavelength. By measuring its temperature, scientists can estimate the mass required to keep it gravitationally confined. Time and again, the numbers reveal far more mass than telescopes can detect directly. This unseen component is what we call dark matter. It does not emit light. It does not absorb it. It interacts primarily through gravity, yet it outweighs ordinary matter by roughly 5 to 1. Without it, galaxies would not hold together. Superclusters would not form. The cosmic web itself would unravel. In the region of the Great Attractor, dark matter likely plays a dominant role. The visible clusters, Norma Centaurus and those within Shapley, are only the luminous peaks of much larger halos of invisible mass. The flows we observe are not responding merely to galaxies. They are responding to a hidden framework stretching across hundreds of millions of light years, and this framework did not appear randomly. It traces back to subtle variations imprinted in the universe when it was still young. To understand why structure exists at all, and why some regions became attractors, we must return once more to the early universe, when the seeds of today's cosmic landscape were first planted, long before galaxies formed, before stars ignited or clusters assembled. The universe was almost perfectly smooth. The cosmic microwave background reveals this remarkable uniformity. Across the sky, its temperature varies by only a few parts in 100,000. At first glance, such smoothness seems incompatible with the dramatic structures we see today: sprawling filaments, dense clusters, immense voids. But those tiny fluctuations were enough. In the early universe, regions that were ever so slightly denser than average contained a bit more mass. Gravity amplified those differences over time. As space expanded, matter did not remain evenly distributed. It slowly gathered where density was higher, pulling in surrounding material. Over billions of years, small variations grew into galaxies, clusters, and superclusters. Dark matter played a decisive role in this process. Because it does not interact with radiation, it began collapsing into structures earlier than ordinary matter. While normal matter was still tightly coupled to light in the hot plasma of the young universe, dark matter was already forming gravitational wells. After the plasma cooled and atoms formed, ordinary matter fell into those pre-existing wells. In this way, dark matter acted as a cosmic scaffold guiding where galaxies would eventually emerge. The Great Attractor is not an anomaly in isolation. It is one node in this vast network. Its mass concentration reflects billions of years of gravitational amplification, beginning with fluctuations imprinted less than 400,000 years after the Big Bang. What we interpret as mysterious pull is the cumulative result of structure formation across cosmic time. Yet even with this understanding, one puzzle remained. If the universe began so uniform, and if gravity operates everywhere the same way, should large-scale motion eventually average out? Or do structures like the Great Attractor suggest that matter is more unevenly distributed than we once believed? To answer that, astronomers needed to examine not just local flows, but the symmetry of the universe itself. Modern cosmology rests on a foundational assumption known as the cosmological principle. On sufficiently large scales, the universe is homogeneous and isotropic. In other words, when averaged over vast distances, matter should be distributed evenly, and no direction in space should be fundamentally preferred. At first glance, the Great Attractor appears to challenge that idea. After all, if enormous structures can influence motion across hundreds of millions of light years, does that not imply a symmetry on a grand scale? The key lies in scale. When we examine regions spanning tens of millions of light-year, structure is obvious. Filaments stretch across space. Clusters gather at their intersections. Voids expand between them. But as we increase the scale to billions of light-years, these variations begin to smooth out statistically. Over sufficiently large volumes, dense regions are balanced by emptier ones. The motion of our galaxy does not indicate that the universe has a central point or a preferred direction. It reflects the fact that we reside within a structured region of space. Just as a valley does not invalidate the existence of flat terrain elsewhere, gravitational basins do not negate large-scale uniformity. Observations from galaxy redshift surveys support this view. When astronomers map the distribution of millions of galaxies, patterns emerge, but no single structure dominates the observable universe. Even the Shapley supercluster, immense as it is, occupies only a small fraction of the cosmic volume. The Great Attractor then is significant locally but not cosmologically exceptional. Still, its gravitational influence raises another subtle question. If structures balance statistically at extreme scales, why does our local group exhibit such a substantial peculiar velocity? Is the combined mass of nearby superclusters sufficient to account for it fully? Or is there something more distant contributing to the flow? Some researchers have proposed a more controversial possibility. Perhaps the motion we observe is influenced not only by structures we can map, but by mass distributions extending beyond the limits of what we can see. In the early 2000s, data from the Wilkinson microwave anisotropy probe led to an unexpected claim. A team analyzing subtle distortions in the cosmic microwave background reported evidence that galaxy clusters across vast distances appeared to share a coherent motion, all drifting in roughly the same direction. They called it the dark flow. Unlike the motion toward the Great Attractor, which can be explained by known nearby mass concentrations, this proposed flow seemed to extend far deeper into space, possibly beyond the scale of mapped superclusters. If true, it suggested that structures outside the observable universe might be exerting gravitational influence on the matter we can see. The implication was profound. The observable universe is limited not by distance alone, but by time. We can see only as far as light has travelled since the Big Bang. If mass exists beyond that horizon arranged unevenly, it could in principle affect the motion of structures within it. But the evidence was subtle, and the measurements extraordinarily delicate. Subsequent analyses using data from the Planck satellite did not confirm the dark flow with the same statistical significance. Some researchers argued that the signal could arise from noise calibration effects, or the inherent difficulty of extracting such minute velocity information from background radiation. Today the dark flow remains debated. Most cosmologists conclude that the observed peculiar velocity of our local group can be explained primarily by known large-scale structures, the combined gravitational influence of Laniakea, the Shapley supercluster, and surrounding density variations. Yet the episode served as a reminder of something essential. We do not see the entire universe, and any map we construct, no matter how detailed, is bounded by a cosmic horizon. For now, the Great Attractor is best understood not as evidence of something beyond physics, but as a feature of the large-scale structure within our observable domain. Still, one final piece remains to complete the picture. If gravity shapes motion, and dark matter shapes structure, what role does the accelerating expansion of the universe play in all of this? In 1998, observations of distant supernovae revealed a discovery that reshaped cosmology. The expansion of the universe is accelerating. Galaxies are not merely moving apart because of the momentum left over from the Big Bang. Space itself is stretching faster over time, driven by a component we call dark energy. On the larger scales, this acceleration dominates the cosmic future. At first, this seems to contradict the idea of large-scale gravitational flows. If expansion is accelerating everywhere, how can superclusters still pull matter inward? The answer lies in scale and timing. Gravity operates most effectively where matter is already concentrated. In dense regions such as galaxy clusters, gravitational binding overcomes expansion. Galaxies within clusters remain bound. In superclusters, the situation is more delicate. Some regions will eventually remain gravitationally connected, while others will slowly drift apart as dark energy takes control. The Great Attractor exists within this balance. Its gravitational basin, formed over billions of years, shaped primarily during epochs when matter dominated cosmic dynamics. But as dark energy becomes increasingly influential, the growth of large-scale structure slows. Over time, distant superclusters will recede beyond causal contact. Their gravitational influence will diminish as space between us expands faster than gravity can bridge. In that sense, the flow of our galaxy is not an eternal journey. It is part of a transitional era in cosmic history, an epoch when matter still shapes motion across hundreds of millions of light years, but not indefinitely. Eventually, the accelerating expansion will isolate gravitationally bound systems from one another. The vast web of filaments and attractors will become less connected. The Great Attractor will remain a feature of our region of space, but it will not grow forever. And this places our motion in a broader temporal context. We are observing and participating in a universe that is still dynamically evolving. The Milky Way is not falling toward a permanent destination. It is responding to the current balance between gravity and expansion in a universe whose structure is still unfolding. Understanding motion on cosmic scales requires more than detecting a single velocity vector. Astronomers must measure distances with precision, separate expansion from local movement, and reconstruct three-dimensional flows from incomplete data. The first step is redshift. As space expands, light from distant galaxies stretches, shifting toward longer wavelengths. This redshift provides a measure of how fast a galaxy is receding due to cosmic expansion. But redshift alone cannot distinguish between expansion and local motion. To isolate peculiar velocity, astronomers must also know the galaxy's actual distance independent of redshift. This is far more difficult. Techniques such as Cepheid variable calibration, Type 1 supernova standard candles, and the Tully-Fisher relation allow researchers to estimate intrinsic distances. By comparing expected expansion velocity to observed redshift, they can determine whether a galaxy is moving slightly faster or slower than the Hubble flow. When these measurements are repeated across thousands of galaxies, patterns emerge. Velocity surveys reveal coherent streaming motions, galaxies drifting together toward dense regions. Statistical reconstruction methods then translate these motions into gravitational potential maps, inferring where mass must be concentrated to produce the observed flows. This approach transformed the study of the Great Attractor. Rather than searching blindly behind the zone of avoidance, astronomers began reconstructing the invisible mass distribution from motion itself. Even where galaxies cannot be directly seen, their trajectories betray the curvature of space around them. In this way, motion becomes a diagnostic tool. We cannot observe dark matter directly. We cannot see through every obscuring region. But by measuring how galaxies move, we can map the gravitational landscape they inhabit. And as the data improved, it became clear that our galaxy's motion is not chaotic. It is a remarkably coherent part of a structured flow embedded within the larger architecture of the cosmic web. When we zoom out far enough, the universe does not resemble a random scatter of galaxies. Large redshift surveys mapping millions of galaxies in 3 dimensions reveal an intricate pattern. Matter is arranged in elongated filaments stretching across hundreds of millions of light years. These filaments intersect at dense nodes where galaxy clusters gather. Between them lie immense voids, regions so underdense that they contain only a fraction of the cosmic average matter. This structure is known as the cosmic web. It emerged naturally from the early density fluctuations amplified by gravity. Over billions of years, matter flowed along gravitational gradients, collecting into sheets and filaments before collapsing into clusters. Dark matter halos formed the backbone. Ordinary matter followed. Within this framework, the Great Attractor is not anomalous. It occupies one of the nodes where multiple filaments converge. The Shapley supercluster, even more massive, lies along the same large-scale filamentary network. Galaxies do not move randomly through this structure. They migrate along filaments drawn toward intersections where gravitational potential is deepest. In this sense, the motion of the Milky Way is not a direct plunge toward a single point. It is a gradual descent along a filament embedded in a vast gravitational landscape. The cosmic web also explains why voids matter. Voids expand faster than average because they contain less mass to slow expansion. As they grow emptier, surrounding matter flows away from them and toward denser regions. This dynamic contributes to the net motion we observe, reinforcing the influence of attractors while amplifying the effect of repellers. The result is a universe that is both structured and dynamic. Galaxies trace the web like dew along strands of an invisible lattice. Their motions reveal not chaos but geometry, a geometry written in dark matter and sculpted over billions of years. The Great Attractor is one feature in that geometry, but to fully grasp its scale, we must place our own galaxy within this immense network, not as an observer, but as a participant. From Earth, it's easy to imagine that we occupy a central vantage point in the universe. After all, every map places us near the middle, but cosmologically our position is neither central nor exceptional. The Milky Way resides in a modest group of galaxies, the local group dominated by 2 large spirals, our own and Andromeda. This group in turn lies along the edge of a filament that connects to larger structures within Laniakea. We are not at the heart of this supercluster. We are near its periphery. Velocity reconstructions show that our local group is drifting along this filament toward denser regions deeper within the gravitational basin. The path is not a straight line toward a single object, but a gradual convergence shaped by multiple mass concentrations distributed across space. At the same time, our galaxy is not only moving toward the Great Attractor region, it is also participating in smaller scale dynamics. Within the local group, the Milky Way and Andromeda are gravitationally bound and moving toward one another. Their eventual merger billions of years from now is governed by local gravity, not supercluster scale flow. This layering of motion is crucial. On small scales, galaxies orbit and merge. On intermediate scales, groups drift toward clusters. On even larger scales, superclusters define gravitational basins. And beyond that, cosmic expansion stretches space itself. Our motion toward the Great Attractor is one component within this hierarchy. We are embedded in multiple gravitational systems simultaneously, like a passenger on a ship that is itself riding an ocean current within a planet that orbits a star inside a galaxy, drifting along a cosmic filament. The illusion of stillness dissolves at every scale, and yet despite the complexity of overlapping motions, the direction defined by the cosmic microwave background remains consistent. The Milky Way is not wandering unpredictably. It is following the geometry of structure, which brings us to an important quantitative question. How much mass does it take to bend the motion of galaxies across such enormous distances? To influence motion across hundreds of millions of light years, gravity must operate on extraordinary scales. Newton's law tells us that gravitational force weakens with the square of distance. Double the separation and the force drops by a factor of 4. On intergalactic scales, where distances are measured in tens or hundreds of millions of light years, this weakening is dramatic. So how can a structure exert measurable influence from so far away? The answer lies not in intensity but in accumulation. A single galaxy cannot alter the trajectory of the local group at such distances. Even a typical cluster would be insufficient. But when mass is distributed across vast regions, thousands of galaxies embedded in enormous halos of dark matter, the combined gravitational potential becomes significant. The Norma cluster alone contains mass equivalent to hundreds of trillions of suns. The Shapley supercluster contains dozens of such clusters packed into a region roughly 200 million light-years across. When astronomers estimate its total mass, the figure approaches 10 quadrillion solar masses. Numbers of that magnitude reshape space. Importantly, gravity does not require direct contact. It acts through curvature, a gradual distortion of space-time across immense distances. The local group does not need to be near Shapley to feel its influence. It simply needs to exist within the extended gradient of its gravitational field. However, calculations suggest that no single structure accounts for the entire measured peculiar velocity of our galaxy. Instead, the motion arises from the integrated effect of multiple mass concentrations nearby clusters, distant superclusters, and the surrounding distribution of dark matter. In other words, the Great Attractor is not a solitary mass exerting a singular pull. It is the name we give to a region where the gravitational potential deepens due to overlapping structures. And when we calculate how matter is distributed across that region, another pattern becomes clear. Visible galaxies are only the luminous traces. Most of the mass shaping this motion remains unseen. If most of the mass influencing our motion is invisible, how can we measure it? Astronomers rely on one of gravity's most subtle effects: gravitational lensing. According to general relativity, mass bends space-time. Light traveling through curved space does not follow a straight path. When distant galaxies lie behind massive structures, their images appear slightly distorted, stretched, sheared, or magnified. By statistically analyzing these distortions across large areas of the sky, researchers can reconstruct maps of total mass distribution, including dark matter. This technique, known as weak gravitational lensing, has transformed cosmology. Instead of counting luminous galaxies alone, scientists can now map the full gravitational landscape. These maps consistently show that dark matter halos extend far beyond visible clusters. Around massive regions like those associated with the Great Attractor and the Shapley supercluster lensing reveals enormous reservoirs of unseen mass. The luminous galaxies are simply the peaks of much larger gravitational mountains. These reconstructions confirm that the flow of galaxies through Laniakea aligns with the gradients in total mass, not just visible matter. Where dark matter density increases, peculiar velocities converge. Where density decreases, motion diverges. In effect, lensing allows us to see the scaffolding that structures the cosmic web, and the picture that emerges is not chaotic. It is coherent. The Great Attractor region corresponds to a genuine concentration of mass embedded within this network. Its influence is measurable not because it violates physics, but because it follows it precisely. Yet even with dark matter included, a subtle question remains. Are we confident that gravity behaves exactly as we assume on these scales? Or is it possible that the laws we apply, tested in laboratories and within galaxies, might require refinement across hundreds of millions of light years? Whenever astronomers encounter missing mass, two broad possibilities arise. Either additional matter exists that we cannot directly detect, or our understanding of gravity is incomplete. Dark matter has become the prevailing explanation because it consistently accounts for observations across multiple scales: galaxy rotation curves, cluster dynamics, gravitational lensing, and the formation of large-scale structure within the standard cosmological model known as lambda-cold dark matter. The Great Attractor and similar structures arise naturally from the growth of density fluctuations over cosmic time. But alternative ideas have been explored. Modified gravity theories such as MOND and its relativistic extensions attempt to explain galactic rotation without invoking unseen matter. In certain contexts, these models reproduce observed dynamics remarkably well. However, when applied to clusters and superclusters, they face greater difficulty. The magnitude of gravitational influence required at those scales typically exceeds what modified gravity alone can provide without reintroducing unseen components. Large-scale structure surveys further strengthen the case for dark matter. Computer simulations that include dark matter and dark energy successfully generate filamentary networks closely resembling the observed cosmic web. Remove dark matter from these models and structure formation slows dramatically. Superclusters like Shapley become far less pronounced. In the case of the Great Attractor, the observed flows align with predictions from the standard model, when known mass concentrations and dark matter halos are included. For now, the simplest explanation remains the most robust. Gravity behaves consistently across scales, and the unseen mass responsible for shaping motion is dark matter distributed along the cosmic web. Still, science remains provisional. As instruments grow more precise and surveys extend deeper into space, even small discrepancies could point to refinements in our understanding. And with that, we return to the broader perspective. If the Great Attractor is not a singular object, not exotic new physics, but a natural consequence of structure formation, what does its existence ultimately tell us about our place in the universe? The Great Attractor does not occupy a privileged position in the cosmos. It does not define a center. It does not mark a boundary. What it reveals instead is something more subtle and more profound. The universe is not static on any scale. Galaxies are not suspended like ornaments in empty space. They are embedded within a dynamic gravitational network constantly responding to the distribution of mass around them. Even vast structures that appear permanent are part of an ongoing process shaped by expansion, collapse, and flow. When we measure the motion of the Milky Way, we are witnessing the accumulated effect of billions of years of cosmic evolution. The peculiar velocity we observe today reflects density contrasts, seeded shortly after the Big Bang amplified by dark matter, organized into filaments and gradually sculpted into superclusters. The Great Attractor is not an anomaly disrupting uniformity. It is evidence that structure exists and that gravity continues to shape it. At the same time, our motion is temporary. In the distant future, dark energy will dominate ever more completely. Structures beyond our gravitationally bound region will drift beyond reach. The cosmic web will thin from our perspective. The broader network that currently guides our flow may eventually fade from view. What remains bound will remain bound. What is not will recede. We happen to live in a cosmic era, when large-scale flows are still measurable, when the gravitational architecture of nearby superclusters remains dynamically relevant. That era will not last forever, and so the Great Attractor is not simply a feature on a map. It is a reminder that we inhabit a universe in transition, one where gravity and expansion are still negotiating the future of structure. But to fully appreciate that, we must step back once more beyond individual superclusters and consider the grand pattern they collectively form. When astronomers assemble maps of galaxy distributions across billions of light years, a remarkable realization emerges. No structure stands alone. Superclusters connect to other superclusters through filaments of dark matter and galaxies. Voids expand between them like expanding bubbles in a cosmic foam. On intermediate scales, the universe appears intricate and uneven. But statistically, when surveyed across enormous volumes, a balance appears. Overdensities are matched by underdensities. Clusters are countered by voids. The Great Attractor, the Shapley supercluster. Laniakea itself, all are local features within a much larger tapestry. Computer simulations of cosmic evolution show that such patterns arise naturally from tiny fluctuations in the early universe. Starting from nearly uniform conditions, gravity amplifies slight differences. Regions that are only marginally denser collapse faster. Over time, a network forms self-organized, interconnected, but not centrally directed. There is no master structure orchestrating motion. There is no cosmic destination drawing everything inward. Instead, matter responds locally to gradients and gravitational potential. On sufficiently large scales, those gradients average out. The motion of the Milky Way is significant within our region of space, but it does not imply that the universe as a whole is flowing toward a single point. There is no universal attractor beyond which all motion converges. What we observe is the consequence of living in a structured patch of an otherwise statistically uniform cosmos, and that perspective reframes the mystery. The Great Attractor is not evidence of something extraordinary breaking the rules. It is evidence that the rules gravity, expansion, structure, formation operate consistently across scales far beyond human intuition. Yet one final question remains. If we project our motion forward through time, where does it lead? Projecting cosmic motion forward is not as simple as extending a straight line. The universe is not static, and neither are the forces shaping it. Gravity pulls inward. Dark energy drives expansion outward. The relative strength of these influences changes over time. Within the local group, the future is clear. The Milky Way and Andromeda are gravitationally bound. In roughly 4 to 5 billion years, they will merge into a single elliptical galaxy. That event is governed by local gravity and will occur regardless of supercluster scale flows. But beyond our immediate neighborhood, the picture becomes more complex. Some portions of Laniakea are gravitationally bound and will remain so. Other regions are only loosely connected. As dark energy continues to accelerate expansion, distant superclusters will recede faster and faster. Eventually, light from them will never reach us again. Their gravitational influence will weaken as space between us stretches. The Great Attractor itself may not remain dynamically relevant forever. While its mass concentration will persist, the accelerating expansion of space will gradually reduce the scale over which gravitational attraction can compete effectively. Structures not already tightly bound will drift apart. In the far future, tens of billions of years from now, observers within our merged galaxy may see a very different sky. Most external galaxies will have faded beyond the cosmic horizon. The vast network that currently defines the cosmic web will no longer be observable. From that vantage point, the Great Attractor would not appear as a destination or even as a detectable structure. It would simply be part of a gravitationally bound remnant embedded in an expanding void. Our present motion, then, is part of a specific cosmological epoch, one in which structure is still visible, still interacting, still shaping the dynamics of galaxies across immense distances. We are living at a time when the cosmic web is not only real but measurable, and that may be rarer than we realize. It is natural to imagine motion as a journey with an end point. If we're moving toward the Great Attractor, then surely we must be going somewhere. But cosmic motion is not like travel across a landscape. There is no fixed coordinate in space that galaxies approach in a straight line. The universe itself is expanding. The reference frame shifts. The gravitational field evolves as structures grow and recede. The local group's peculiar velocity is measured relative to the cosmic microwave background, a relic radiation field that defines a kind of universal rest frame. In that frame we are moving, but the mass concentrations influencing that motion are not stationary in any absolute sense. They too participate in the expansion of space and in their own local gravitational dynamics. The Great Attractor is not waiting at the end of a trajectory. It is part of a continuously evolving gravitational landscape. Over billions of years, as matter flows and structures reorganize, the depth and shape of that landscape change. Filaments merge, clusters interact, voids expand. The gradient's guiding motion shifts subtly over time. What we call a pull is simply the present configuration of mass. There is no cosmic waterfall where galaxies accumulate in a final basin. There is only ongoing redistribution gravity competing with expansion in a universe that never truly settles into equilibrium. From our perspective, the Milky Way is descending along a gravitational slope defined by surrounding mass concentrations. But the slope itself is not fixed. It evolves, and that realization brings us back to the beginning. The mystery was never about a hidden object exerting extraordinary power. It was about understanding how motion arises in a universe governed by simple laws applied across unimaginable scales. When the Great Attractor was first proposed, it carried an air of mystery, a suggestion that something unseen and possibly exotic was dragging entire galaxies through space. But as observations accumulated, the narrative changed. The mystery did not disappear, it matured. What once seemed like a singular gravitational anomaly is now understood as part of a broader structural framework. The flows measured in galaxy surveys, the mass revealed through gravitational lensing, and the architecture mapped by redshift catalogues all point toward the same conclusion. Our motion is the natural outcome of living inside a structured universe. There is no hidden monster behind the Milky Way's disk. There is no violation of physical law. There is only gravity acting over immense distances, amplified by dark matter, moderated by dark energy, and expressed through the geometry of the cosmic web. Yet the story remains compelling, not because it overturns cosmology, but because it demonstrates how much we can infer from subtle signals. A temperature difference of a few millionths of a degree in ancient radiation was enough to reveal that our galaxy is moving. From that tiny anisotropy, we reconstructed a three-dimensional map of mass spanning hundreds of millions of light years. The Great Attractor is not a failure of understanding. It is an example of how understanding grows. Each refinement in measurement reshaped the question. First, are we moving? Then, toward what? Then, how much mass? Then, how does this fit into the cosmic web? And now the question is broader still. What does it mean to inhabit a universe where even galaxies are not at rest, where motion is layered across scales and structure emerges from nearly perfect uniformity? We often speak of the universe as something we observe, but the Great Attractor reminds us of something more immediate. We are not watching the cosmic web from a distance. We are embedded within it. Every star in the Milky Way orbits within a dark matter halo. That halo moves within the local group. The local group drifts within Laniakea. Laniakea participates in the larger pattern of filaments and superclusters. At every scale, motion is inherited from something larger. There is no absolute stillness anywhere in this hierarchy, and yet these motions do not feel chaotic. They are governed by the same equations that describe falling objects on Earth gravity, operating across vastly different scales. The mathematics does not change, only the distances and masses do. From our vantage point, the sky appears calm. Constellations maintain their shapes over human lifetimes. The Milky Way arches quietly overhead. But beneath that apparent stability, the galaxy is travelling hundreds of kilometres per second relative to the cosmic microwave background. Our solar system orbiting within the Milky Way carries us along. Even as you listen to this, Earth rotates, orbits the Sun, and together we drift through a gravitational landscape shaped billions of years ago. The Great Attractor is not something out there pulling on a stationary universe. It is part of the environment we inhabit, a structural feature of the cosmic terrain, and understanding it changes how we interpret the night sky. The stars are not fixed lights pinned to a dome. They are markers on a moving platform inside a galaxy, descending through a web of invisible mass. The universe is not still. It is structured motion. When we ask what is pulling our galaxy, we are really asking something deeper. How large can structure become in a universe that began almost perfectly uniform? The Great Attractor occupies a region spanning tens of millions of light years. The Shapley supercluster extends even farther. Laniakea stretches across roughly 500 million light years. These numbers strain intuition, yet they remain small compared to the observable universe, which spans more than 90 billion light years in diameter. On those larger scales, structure begins to smooth out. Galaxy surveys show that beyond certain distances, clustering statistics stabilize. The universe approaches homogeneity. No direction dominates. No supercluster defines a universal center. The Great Attractor is significant to us because we are near it. To a distant observer in another filament, a different concentration of mass would define their peculiar motion. This relativity of perspective is essential. There is no preferred vantage point in cosmology. Every observer sees expansion centered on themselves. Every region experiences local gravitational gradients shaped by its surroundings. The Great Attractor is part of our local story, not the universe's ultimate structure. And yet local stories matter. They reveal how general principles manifest in specific places. They show how simple initial conditions give rise to complexity. They demonstrate that even subtle fluctuations in the early universe can evolve into structures capable of guiding galaxies across unimaginable distances. What began as a faint temperature, a symmetry, and ancient radiation became a map of motion. That motion led us to hidden clusters. Those clusters revealed a filamentary network, and that network showed us that we are not suspended in emptiness, but woven into a gravitational tapestry. The question is no longer whether something is pulling our galaxy. It is how elegantly the universe organizes motion without ever requiring a central command. At first, the Great Attractor sounded like a mystery waiting for a dramatic reveal. But the deeper we looked, the more the mystery shifted from what is it to how does this fit. It fits into a universe where gravity amplifies tiny fluctuations. It fits into a cosmos dominated by dark matter. It fits into a large-scale web of filaments and voids. It fits into an era where matter still shapes motion even as dark energy accelerates expansion. The Great Attractor does not break the cosmological principle. It does not imply a cosmic center. It does not require exotic new physics. Instead, it confirms something subtle but powerful. Structure on immense scales is real, measurable, and dynamically relevant. From a temperature difference of a few millionths of a degree in the cosmic microwave background, we inferred a velocity. From that velocity, we reconstructed a gravitational gradient. From that gradient, we uncovered a landscape of mass hidden behind our own galaxy. The process was incremental. Each observation refined the previous one. Each new survey added resolution. What once seemed like a singular unseen object resolved into a network of overlapping structures. The Great Attractor is not a singular destination in space. It is a reminder that even galaxies participate in larger flows, and that those flows are governed by the same fundamental laws that shape falling objects, orbiting planets, and rotating stars. And perhaps most importantly, it reminds us that the universe is comprehensible. Not because it is simple, but because its complexity emerges from consistent principles applied across vast scales, which leaves us with one final reflection. For most of human history, we believed the Earth was fixed. Then we learned it rotates. Then we learned it orbits the Sun. Then we discovered the Sun orbits the center of the Milky Way. Now we know the Milky Way itself is moving not aimlessly, but along the contours of a gravitational landscape shaped billions of years ago. The Great Attractor is not a monster hidden in darkness. It is not a cosmic anomaly waiting to overturn physics. It is structure. It is the natural consequence of matter responding to gravity across immense distances. It is a region where the density of the cosmic web deepens, guiding the flow of galaxies through space. And we are part of that flow. As Earth spins beneath our feet as the Sun carries us around the galactic center, the entire Milky Way drifts through Laniakea, descending along gradients defined by dark matter and ancient fluctuations in the early universe. Nothing in the cosmos is truly at rest. Not planets, not stars, not galaxies. The night sky appears stable only because our lives are brief compared to cosmic time. But on larger scales, motion is continuous and layered, a choreography governed by gravity and expansion. The Great Attractor does not pull us toward a final destination. It reveals that we inhabit a universe of structure, a universe where even galaxies are participants in a vast evolving pattern. And in that realization, the mystery transforms. What once seemed like a hidden force becomes something far more profound. The universe is not still, it is in motion, and so are we. When we mapped the Great Attractor, we discovered that our galaxy is not drifting alone. It is embedded in a vast cosmic web of filaments and clusters, stretching across hundreds of millions of light years. But that discovery leads to a deeper question. If the universe can build structures that large, how large can structure become? Astronomers have identified immense formations, superclusters, great walls, filaments spanning more than 1 billion light years. Some appear so vast that they challenge our intuition about uniformity in the cosmos. Are these truly the largest structures the universe can create? Or is there a natural limit, a scale beyond which gravity can no longer compete with cosmic expansion? Tonight we explore the architecture of the universe itself to ask a fundamental question. What is the largest structure the cosmos can build before expansion tears it apart? Before we search for the largest structure in the universe, we have to clarify what largest actually means. In everyday language, size sounds simple. Bigger means wider, heavier, more extended. But in cosmology, scale can be defined in several fundamentally different ways. Do we mean the largest object by physical diameter, the most massive structure by total mass, or the largest region that is gravitationally bound, meaning it will remain intact despite the expansion of space? These distinctions matter. A structure can span billions of light years and still not be a single coherent object. It may only appear continuous because galaxies trace a filament that happens to align across our line of sight. Another structure may be smaller in diameter, but far more massive and dynamically connected. The cosmic web complicates intuition. Galaxies do not form isolated islands. They cluster along filaments that connect nodes across vast distances. These filaments can stretch for hundreds of millions of light years, linking superclusters together into enormous walls of galaxies. When we map them, they look like continuous structures. But continuity does not necessarily mean unity. To determine what truly qualifies as the largest structure, we must ask a deeper physical question. What does gravity actually hold together? Because in a universe where space itself expands, true structure is not defined by visual scale alone. It is defined by whether gravity can overcome expansion, and that boundary, the limit where structure stops growing, is where our investigation begins. In the early universe, gravity had the upper hand. Matter was denser, galaxies were closer together. Small fluctuations in density could grow efficiently, because the expansion of space, though rapid, was slowing over time due to the gravitational pull of matter itself. Structures formed hierarchically. Small halos collapsed first. They merged into larger halos. Clusters assembled. Filaments thickened. Over billions of years, the cosmic web took shape, but the balance shifted. As the universe expanded, matter became more diluted. Roughly 5 billion years ago, dark energy began to dominate the large-scale dynamics of the cosmos. Expansion stopped slowing down and started accelerating. This transition changed everything. Gravity still binds galaxies within clusters. It still governs mergers and local flows, but on sufficiently large scales, expansion now wins. Two regions that are too far apart will never collapse toward each other, no matter how long we wait. This introduces a natural limit. There exists a maximum scale beyond which structure cannot grow. If a region is not already gravitationally bound, the accelerating expansion of space will pull it apart faster than gravity can bring it together. Cosmologists describe this boundary in terms of a turnaround radius. It marks the distance at which the inward pull of gravity balances the outward expansion of space. Inside that radius, matter can collapse. Outside it, expansion dominates. The largest structures that will ever exist are those that formed before dark energy took control, or those that are already sufficiently bound to resist it. So when we look at enormous formations like the Sloan Great Wall, or even larger proposed cosmic structures, we must ask, are these truly single coherent entities, or are they temporary alignments in a universe that is slowly stretching beyond connection? In 2003, data from the Sloan Digital Sky Survey revealed something extraordinary. A colossal arrangement of galaxies stretching across roughly 1 billion light-years, a structure so vast it dwarfed previously known superclusters. It was named the Sloan Great Wall. At first glance, it appeared to challenge expectations about cosmic scale. If the cosmological principle predicts uniformity on large scales, how could a feature this enormous exist? But appearance can be deceptive. The Sloan Great Wall is not a single gravitationally bound object. It is a complex of interconnected clusters and filaments, a segment of the cosmic web that happens to align in a way that makes it appear continuous in large-scale surveys. Its immense length does not imply that gravity binds it as a whole. Instead, it represents an overdense region where filaments converge, traced by galaxies that formed along pre-existing dark matter scaffolding. Within it, individual clusters are gravitationally bound. The wall itself, however, is not a solid entity. Over cosmic time, its components will not collapse into one unified structure. This distinction is crucial. The universe can produce visually striking patterns spanning enormous distances, but the true limit of structure is determined not by visual continuity but by dynamical cohesion. The Sloan Great Wall is one of the largest mapped features in the observable universe, yet it may not qualify as a single object in the physical sense, and it is not the only candidate. In the years that followed, astronomers identified even larger proposed formations, some so vast they seemed to push against the statistical limits of cosmic uniformity itself, which raises an even more provocative question. How large can a pattern become before it stops being meaningful as a structure at all? In 2014, astronomers analysing gamma-ray burst distributions reported evidence for something even larger than the Sloan Great Wall. They identified a clustering of events spanning an estimated 10 billion light-years across a region of the sky in the direction of the constellations Hercules and Corona Borealis. If interpreted as a coherent structure, it would rank among the largest features ever proposed, rivaling a significant fraction of the observable universe. The claim immediately sparked debate. Gamma-ray bursts are rare, powerful explosions associated with massive stellar deaths or compact object mergers. Because they can be detected at extreme distances, they serve as probes of large-scale structure, but they're also sparse and unevenly sampled. Statistical fluctuations can appear as clustering when the dataset is limited. Was this enormous feature a genuine cosmic wall or a product of limited statistics? Subsequent analyses suggested caution. While the clustering was intriguing, its statistical significance remained contested. unlike galaxy redshift surveys that map millions of galaxies in 3 dimensions. Gamma-ray burst data provide a much sparser picture of the universe's structure. Even if such a structure exists, another question follows. Would it be gravitationally connected, or would it merely represent a region where density fluctuations happen to align on very large scales? Cosmological simulations based on the Standard Model allow for rare large features to emerge from random initial conditions, but as scale increases, the probability of truly coherent bound structures decreases rapidly. The Hercules Corona Borealis feature may be a remarkable statistical pattern, but not necessarily a single cosmic object. And this tension reveals something important. There is a difference between visual scale and physical unity. The universe can generate enormous patterns, but gravity places limits on what can truly remain together. To understand those limits, we must move from observation to theory, from mapping walls to calculating what gravity can realistically bind in an accelerating cosmos. To determine whether a structure is truly unified, cosmologists rely on dynamics rather than appearance. The key concept is the turnaround radius. Imagine a spherical region of matter embedded in the expanding universe. At large distances, space carries matter outward with the Hubble flow, but if the region contains enough mass, its gravity can counteract expansion locally. At some critical boundary, the outward expansion and inward gravitational pull exactly balance. That boundary defines the maximum size of a gravitationally bound system. Inside it, matter can collapse or remain bound indefinitely. Outside it, expansion wins. Material beyond that limit will never fall inward no matter how much time passes. In a universe dominated by dark energy, this limit becomes even stricter. Dark energy behaves as a constant energy density of space itself. As space expands, its influence does not dilute. Over time, it becomes increasingly dominant, accelerating expansion and shrinking the effective scale on which gravity can overcome it. For a structure of a given mass, there is a theoretical maximum turnaround radius, a scale beyond which binding is impossible. When astronomers apply this reasoning to superclusters, the result is striking. Most superclusters, including Laniakea, are not fully gravitationally bound as a whole. Their internal clusters may remain connected, but the entire structure will not collapse into a single object. Instead, it will gradually fragment into smaller bound units. This reveals a fundamental truth. The largest structures we can map are not necessarily the largest structures that can survive. Visual grandeur does not guarantee dynamical cohesion. The universe may allow enormous patterns to emerge, but it sets strict limits on what gravity can ultimately hold together, and those limits define the true maximum scale of structure. To explore the limits of cosmic architecture, astronomers turn to simulations. Using the known laws of gravity, the measured abundance of dark matter, and the accelerating expansion driven by dark energy, researchers can evolve the universe forward in time inside powerful supercomputers. These simulations begin with the tiny density fluctuations observed in the cosmic microwave background and allow them to grow under gravity. The result is a digital universe. Filaments emerge, clusters collapse, voids expand. The simulated cosmic web closely resembles what galaxy surveys reveal, an encouraging confirmation that the underlying physics is correct. But simulations do more than reproduce the present. They project the future. When dark energy becomes dominant, large-scale growth slows dramatically. New superclusters stop forming. Existing filaments thin as expansion stretches them. Only regions that are already gravitationally bound remain intact. In these models, the largest long-term structures are not superclusters spanning hundreds of millions of light-years. They are smaller, tightly bound clusters and groups. Over tens of billions of years, the cosmic web gradually dissolves into isolated island universes, gravitationally self-contained systems separated by expanding voids. This means that many of the largest structures we observe today are temporary alignments in cosmic history. They exist because we live in an epoch when gravity still competes effectively on large scales. but their coherence will not persist indefinitely. The universe is still organizing itself, but that era has a deadline, so the question shifts again. If expansion ultimately limits structure, is there a theoretical maximum size that gravity can ever assemble even briefly before dark energy prevents further growth? To answer that question, cosmologists examine a critical concept, the homogeneity scale. If you zoom out far enough, the universe begins to look statistically smooth. Local clustering fades into uniformity. The density variations that create filaments and walls become minor fluctuations around a cosmic average. Observations suggest that this transition occurs on scales of roughly 100 to 300 megaparsecs, several hundred million light years. Below that scale, structure is pronounced. Above it, the universe approaches homogeneity. This does not mean that no large features exist beyond that distance. It means that when averaged over sufficiently large volumes, those features balance out. Overdense regions are offset by voids. No preferred direction or dominant structure persists. The homogeneity scale provides an important constraint. If the universe becomes statistically uniform beyond a certain distance, then structures significantly larger than that scale must be rare. Statistical extremes, not the norm, and their gravitational coherence becomes increasingly unlikely. In simulations consistent with the standard cosmological model, the largest gravitationally bound systems rarely exceed a few tens of megaparsecs. Superclusters may span hundreds of megaparsecs visually, but only smaller subregions within them are truly bound. This suggests a natural ceiling. Gravity can assemble enormous networks, but only up to a scale where expansion and initial conditions allow density fluctuations to grow coherently. Beyond that, the universe smooths out. The great walls we observe are impressive, but they exist within this statistical framework. They are peaks in a distribution, not violations of uniformity. And this brings us closer to a boundary, not a physical wall, but a limit defined by the interplay of initial fluctuations, dark matter, and cosmic expansion. The universe can build very large structures, but it cannot build infinitely large ones. For a time, some researchers proposed a radical alternative. What if structure never truly smooths out? What if the universe is fractal, meaning patterns repeat at every scale with no transition to homogeneity? In a fractal universe, there would be no larger structure. Clusters would connect to superclusters, which would connect to even larger networks indefinitely. Density would never average out. The concept of a homogeneity scale would disappear. At first glance, the existence of enormous features like the Sloan Great Wall seem to support this idea, but extensive surveys over the past 2 decades have tested it carefully. Projects such as the 2-degree field Galaxies survey and the Sloan Digital Sky survey mapped millions of galaxies across vast volumes. When researchers applied statistical tools, correlation functions, power spectra, and scaling analyses, the data showed a clear transition. On sufficiently large scales, matter distribution approaches uniformity. The universe is not fractal at all scales. Instead, it behaves fractal-like only below the homogeneity threshold. Beyond that, clustering weakens and the density field stabilizes around a cosmic average. This result reinforces the cosmological principle and places constraints on how large, coherent structure can become. The cosmic web has texture, but that texture has a limit. Large walls and filaments can form, but their size distribution follows predictable statistics derived from the initial conditions of the early universe. The universe builds structure hierarchically, but not endlessly. There is no infinite nesting of ever larger patterns, and that realization refines our original question. We are not searching for the biggest structure we can imagine. We are searching for the largest structure gravity can plausibly assemble before the smoothness of the cosmos takes over. To understand why structure has limits, we must return once more to the beginning. The universe did not start with large contrasts in density. The fluctuations imprinted in the cosmic microwave background were tiny variations of roughly 1 part in 100,000. These small irregularities served as seeds for all subsequent structure, but their amplitude was finite. Gravity amplifies differences over time, yet it cannot create contrast where none exists. Regions that were only slightly denser than average could grow into galaxies and clusters. Regions that were slightly underdense expanded into voids. The scale and distribution of those early fluctuations determine the larger structures that can form later. Cosmological measurements reveal that the primordial fluctuations followed a nearly scale-invariant spectrum, meaning variations existed on many scales, but their strength decreased gradually at larger wavelengths. This statistical pattern constrains how pronounced large-scale structure can become. In simulations using these initial conditions, enormous walls and filaments occasionally appear, but their size is bounded by the spectrum of early fluctuations. Structures much larger than the homogeneity scale become increasingly improbable. The universe is not constructing arbitrarily large patterns from nothing. It is evolving a specific set of initial conditions forward in time. Dark matter provides the scaffolding. Gravity provides the amplification. Dark energy eventually halts further growth. Together, these ingredients define the architecture of the cosmos. The largest structures we observe today are not accidental anomalies. They are the natural outcome of those original fluctuations filtered through billions of years of expansion and collapse. And that means the limit on structure is written into the universe from the start. But there is still one final boundary to consider, a boundary not set by physics alone, but by observation itself. Even if the universe contains structures larger than anything we have mapped, there is a fundamental constraint on what we can ever know. Light travels at a finite speed. The observable universe is limited by the distance light has had time to travel since the Big Bang. This boundary, the cosmic horizon, defines the maximum region we can access observationally. Beyond it, space may continue indefinitely. Structures may extend farther, but no signal from those regions has reached us, and none ever will if expansion continues accelerating. This means the largest structure is always defined relative to what we can observe. Within our observable volume, galaxy surveys and cosmic microwave background measurements show no evidence of structure dominating on scales comparable to the entire horizon. The distribution of matter remains statistically uniform when averaged over sufficiently large distances. If there were a single coherent structure spanning a substantial fraction of the observable universe, it would imprint detectable signatures and isotropies in the CMB large deviations in galaxy clustering, or unusual flows inconsistent with known mass distributions. We see none of these at the required magnitude. The universe may be vastly larger than what we observe, perhaps even infinite, but within the observable domain structure has clear statistical limits. So the question of the largest structure becomes twofold. What is the largest structure gravity can build, and what is the largest structure we can ever detect? The answer to both is constrained not only by expansion and dark energy, but by the finite age of the cosmos itself. And when we combine these constraints, a clearer picture begins to emerge. When we combine theory, simulations, and observation, a consistent conclusion emerges. The universe can assemble structures spanning hundreds of millions of light years. It can produce great walls, enormous filaments, and vast supercluster complexes, but most of these are not single gravitationally unified systems. Over the next tens of billions of years, dark energy will continue to accelerate expansion. Regions that are not already gravitationally bound will drift apart irreversibly. Filaments will thin. Superclusters will fragment into smaller stable units. The structures that will ultimately survive are far more modest in scale. Galaxy groups, galaxy clusters, dense cores within superclusters. These are the largest entities whose gravity is strong enough to resist the accelerating expansion of space. Their internal motions will remain bound long after distant galaxies fade beyond the cosmic horizon. Everything larger is temporary. The Sloan Great Wall will not collapse into a single object. Laniakea will not merge into a unified superstructure. The cosmic web as we currently observe it represents a transitional era, a period when matter still competes effectively with dark energy on intermediate scales. In the distant future, observers inside a gravitationally bound remnant will see a much emptier universe. The grand architecture of the web will no longer be visible. What we call large-scale structure today will have dissolved into isolated islands. This reveals the true limit. The largest permanent structures the universe can build are not the most visually dramatic ones. They are the ones gravity can hold together indefinitely, and that boundary is far smaller than the vast walls that first inspired awe in galaxy surveys. The universe builds grand patterns, but only some endure. When we step back from individual discoveries, the Great Attractor, the Sloan, Great Wall, the largest proposed superstructures, a coherent pattern appears. The universe allows complexity, but within constraints. Gravity amplifies initial fluctuations, but only those that existed in the beginning. Dark matter enables structure to grow, but only up to scales supported by those primordial conditions. Dark energy accelerates expansion, placing an eventual ceiling on growth, and statistical homogeneity ensures that beyond a certain distance clustering averages out. There is no runaway hierarchy, no endless stacking of ever larger walls, no infinite fractal extending without bound. The largest gravitationally meaningful structures form within a specific window of cosmic time, after matter dominates expansion, but before dark energy suppresses further collapse. We live inside that window. That is why the cosmic web appears so intricate. That is why enormous walls and filaments exist at all. And that is why their scale has limits. The question that began with the Great Attractor, what is pulling our galaxy, led us outward into ever larger patterns. But the deeper insight is not about any single structure, it is about balance. The universe is shaped by competing influences. Gravity pulling inward, expansion pushing outward, and initial conditions setting the scale of variation. The largest structures emerge where those forces intersect, and they stop growing when the balance shifts. There is grandeur in that restraint. The cosmos does not build without limit. It builds precisely as much structure as its laws allow, no more, no less. If we project this balance far into the future, the picture becomes even clearer. As dark energy continues to accelerate, the expansion of space distances between unbound structures will grow exponentially. Light from distant galaxies will stretch to longer wavelengths, eventually fading beyond detectability. The cosmic microwave background itself will redshift into near invisibility. The vast web we currently observe, filaments connecting clusters across hundreds of millions of light-years, will not remain accessible. Only gravitationally bound systems will endure. Galaxy clusters will remain intact. Groups of galaxies will merge internally. Over time, many bound systems will evolve into single, massive elliptical galaxies surrounded by dark matter. Halos, isolated remnants of what was once an interconnected network. Cosmologists sometimes refer to this future as an era of island universes. Each gravitationally bound region becomes effectively alone, surrounded by expanding emptiness. Observers within such a region billions of years from now would see no evidence of large-scale structure. They might not even detect cosmic expansion. The broader universe would lie beyond their observational horizon. In that distant epoch, the question of the larger structure would have a very different answer. The largest structure would be whatever remained gravitationally bound locally. Everything else would be causally disconnected. This perspective transforms how we interpret what we see today. The cosmic web is not permanent architecture. It is a snapshot taken during a specific phase of cosmic evolution, a time when gravity still weaves filaments, and dark energy has not yet pulled them apart irreversibly. We are observing the universe in one of its most structurally rich eras, and that era will not last forever. There is one final limit that shapes our understanding of cosmic architecture, not a physical boundary imposed by gravity or dark energy, but a limit imposed by knowledge itself. We are confined to the observable universe. No matter how powerful our telescopes become, we cannot see beyond the region from which light has had time to reach us. And because expansion is accelerating parts of the universe that are currently visible, will eventually slip beyond our cosmic horizon. This means that even if structures larger than anything we have mapped exist beyond our observational boundary, they are forever inaccessible to us. Within the observable universe, surveys reveal no dominant structure spanning a significant fraction of the horizon. Statistical homogeneity holds. The largest mapped walls and filaments occupy only small portions of the total volume, so the largest structure we can meaningfully discuss is bounded twice. First by physics, by the scale at which gravity can overcome expansion. Second by observation, by the finite size of the region we can detect. Together these constraints define a maximum. The universe may be infinite. It may extend far beyond what we see, but within our observable domain structure has limits that are both measurable and theoretically grounded. And that realization reshapes the original sense of mystery. The question is no longer whether the universe can build endlessly larger formations. It is how elegantly its laws define where growth stops. We began with a galaxy in motion. The Great Attractor revealed that the Milky Way is not stationary, but descending along a gravitational gradient shaped by large-scale structure. That discovery expanded our perspective from local clusters to superclusters, from filaments to the cosmic web itself. Now the question has shifted, not what is pulling us, but how far structure can extend before the rules of the universe impose a boundary. The answer is not dramatic, it is mathematical. The scale of initial fluctuations limits how much contrast gravity can amplify. The homogeneity scale limits how far clustering remains statistically significant. Dark energy limits how large a bound system can grow. The cosmic horizon limits what we can ever observe. Each constraint narrows the possibilities. The universe can build vast patterns, but only within these frameworks. It cannot generate arbitrarily large coherent objects. It cannot form superstructures that defy expansion indefinitely. It cannot sustain connectivity beyond gravitational binding. This does not diminish the grandeur of cosmic architecture, it refines it. The web we observe is not accidental excess. It is the largest structure the universe can produce under its physical laws during this epoch of cosmic history. And recognizing that boundary brings clarity to the entire journey, from the motion of our galaxy to the limits of cosmic construction. But there is still one final reflection to draw from this exploration. It is tempting to equate size with significance. The larger a structure, the more profound it seems. 1 billion light-years inspires more awe than 1 million. A supercluster feels more meaningful than a cluster. A great wall sounds more impressive than a filament. But cosmology teaches a different lesson. The universe does not strive for maximum scale. It evolves according to balance. Gravity amplifies contrast, but only from seeds that already exist. Dark matter enables structure, but only within the statistical spectrum set at the beginning. Dark energy suppresses growth not abruptly, but gradually ensuring that structure formation is finite. What we observe today is not the result of unchecked accumulation. It is the product of competing influences reaching temporary equilibrium. The largest structures are not infinite because the universe does not permit infinity in practice, even if space itself may be infinite in extent. Laws impose ceilings. Expansion imposes deadlines. Initial conditions impose scale. This is not limitation in a negative sense. It is coherence. The cosmic web is intricate precisely because it formed within defined boundaries. Too little gravity and structure would never emerge. Too much and everything would collapse too quickly. Too much dark energy early on and clustering would be suppressed entirely. Instead, we inhabit a universe tuned not in a mystical sense, but in a dynamical one to allow structure to flourish temporarily, then stabilize. The largest structure the universe can build is not arbitrary. It is determined by the same principles that govern the motion of a falling object and the orbit of a planet, an understanding that reveals something profound. Grandeur in the cosmos is not about excess, it is about balance. If we could compress cosmic history into a single day, large-scale structure would appear late in the afternoon. For billions of years after the Big Bang, matter gradually accumulated into halos and clusters, filaments thickened, voids expanded. The web became increasingly pronounced, but this growth was never destined to continue indefinitely. Dark energy ensures that the era of active structure formation is finite. We happen to live during the peak of that era, a time when the cosmic web is fully developed and still observable across enormous distances. In earlier epochs it was less mature, in later epochs it will fade from view. This means that the larger structures we can map today represent a transitional maximum. They are not permanent monuments. They are phase-dependent features of cosmic evolution. The Great Walls and superclusters exist because we observe the universe during a specific window, when gravity has had time to amplify initial fluctuations, but dark energy has not yet erased large-scale connectivity. Billions of years from now, future observers may see only their local gravitational island. They may have no evidence that superclusters ever connected across hundreds of millions of light years. From their perspective, the largest structure in existence would be whatever remains gravitationally bound locally. The cosmic web as we know it would be a relic of the past, and that realization reframes the search for the largest structure. We are not merely measuring spatial extent. We are witnessing a temporary architecture, one that reflects the universe's present balance of forces rather than an eternal design. So how large can the universe build? Large enough to move galaxies across hundreds of millions of light years. Large enough to weave filaments into walls stretching 1 billion light years or more. Large enough to organize matter into a web that spans the observable cosmos, but not large enough to escape its own laws. Gravity cannot overcome expansion beyond a certain scale. Initial fluctuations cannot generate arbitrarily massive contrasts. Dark energy prevents unbounded growth. The largest structures are therefore not limitless constructions. They are the maximum expression of structure permitted by the conditions of this universe, and that conclusion carries an unexpected elegance. We began with motion, the realization that our galaxy is falling through space. That led us to hidden mass superclusters and the cosmic web. Then the question expanded outward. If such immense structures exist, where does the hierarchy end? It ends where balance is restored. Beyond the homogeneity scale, the universe smooths statistically. Beyond the turnaround radius, gravity loses to expansion. Beyond the cosmic horizon, observation stops entirely. The universe is vast. It may even be infinite, but structure within it is not unbounded. There is a larger scale of meaningful coherence, and it is defined not by imagination but by physics, which brings us to the final perspective. It is easy to speak about the cosmic web as though we are standing outside it examining a diagram, but we are inside the structure we describe. Our galaxy moves within a filament. That filament connects to clusters. Those clusters reside within larger overdense regions. The motion of the Milky Way that once seemed mysterious now appears as a natural consequence of embedded geometry. The larger structures in the universe are not distant abstractions. They shape the motion of the galaxy that contains every star we have ever seen. Yet from our vantage point, the sky appears calm. Constellations hold their positions. The Milky Way drifts slowly overhead. The scale of cosmic architecture is so immense that its dynamics are imperceptible over human timescales. This contrast between apparent stillness and underlying motion defines cosmology. The Great Attractor revealed that we are moving. The cosmic web revealed that we are connected. The limits of structure reveal that this connectivity has boundaries. The universe is neither chaotic nor unbounded in its construction. It is organized, evolving, and finite in its capacity to build coherent form, and perhaps that is the most important insight. We do not inhabit an endless fractal of ever-growing complexity. We inhabit a cosmos where structure emerges, reaches its peak, and gradually yields to expansion. Understanding that does not diminish the scale of the universe. It clarifies it, and in that clarity, the question of the largest structure transforms from a search for excess into an appreciation of balance. In the end, the search for the largest structure in the universe is not about finding something bigger than everything else. It is about understanding where growth stops. The Great Attractor showed us that motion on immense scales is real. The Sloan Great Wall demonstrated that matter can align across staggering distances. Proposed superstructures pushed our imagination to the edge of the observable universe, but each time we examined them more closely, the same pattern emerged. They are impressive yet constrained, vast yet temporary, coherent yet not unbounded. Physics draws the lines. Gravity organizes matter but only where density allows. Dark matter scaffolds structure but only from primordial seeds. Dark energy limits further growth. Statistical homogeneity ensures no single structure dominates the cosmos. The largest architecture the universe can build is not infinite. It is finite, evolving and governed by equilibrium, and perhaps that is the deeper lesson behind both the Great Attractor and the cosmic web. The universe does not construct without restraint. It does not spiral into unlimited accumulation. It builds within limits set at its birth and shaped by its expansion. Grandeur in cosmology is not about endless scale. It is about scale that makes sense. Imagine the universe tens of billions of years from now. Dark energy has stretched space so dramatically that distant superclusters have slipped beyond visibility. The cosmic microwave background has redshifted into wavelengths too long to detect. The once intricate network of filaments is no longer observable. What remains are gravitationally bound remnants, dense clusters and merged galaxies, isolated in expanding darkness. From within one of those remnants, the idea of a cosmic web would be inaccessible. There would be no visible evidence of vast superclusters, no great walls traced by millions of galaxies, no large-scale flows measurable against ancient radiation. The largest structure from that future perspective would simply be the local bound system. This thought experiment reveals something profound. Our understanding of cosmic structure is not only limited by physics, it is limited by epoch. We live at a time when the web is still visible, when the largest patterns of matter can still be mapped, when gravity and expansion are still in measurable competition. That will not always be true. The cosmic architecture we analyze today is a transient arrangement in a universe that continues to evolve. So when we ask about the largest structure the universe can build, we are really asking about the maximum expression of structure during this specific phase of cosmic history, and that realization completes the arc that began with a galaxy in motion. The largest structure in the universe is not simply a number measured in light years. It's a feature of timing. If intelligent observers had emerged billions of years earlier, the cosmic web would have been less developed. Superclusters would have been smaller. The Great Walls would not yet have fully formed. The maximum scale of visible structure would have been more modest. If observers arise billions of years later, much of today's large-scale structure will have vanished beyond the horizon. They may infer a smaller universe, perhaps even a static one, unaware of the larger network that once existed. We occupy a narrow window, a period when structure has matured but not yet dissolved. This temporal positioning shapes our conclusions. It allows us to map filaments spanning hundreds of millions of light years. It allows us to measure peculiar velocities against the cosmic microwave background. It allows us to test homogeneity and calculate turnaround radii. In another epoch, these measurements would be impossible. So the larger structure is not only constrained by gravity and expansion, it is constrained by what our cosmic moment permits us to observe. We see the universe at near maximum structural richness. That does not mean the cosmos is centered on us. It means we exist during a dynamically revealing phase, and that context reframes everything. The Great Attractor was never just about motion. The search for the largest structure was never just about size. Both are reflections of a deeper truth. We are measuring the universe at the peak of its architectural expression. The search for the larger structure began with a sense of scale, with walls and filaments stretching farther than intuition comfortably allows. But in tracing their limits, something more subtle emerged. Structure is not accidental decoration. It is the natural response of matter to gravity within a finite set of initial conditions. The cosmic web is not an anomaly layered onto an otherwise empty universe. It is the inevitable outcome of tiny fluctuations amplified over billions of years. And yet that inevitability has boundaries. The web does not thicken without limit. Superclusters do not merge endlessly. Walls do not grow until they fill the cosmos. Instead, structure rises, peaks, and stabilizes within constraints imposed by dark energy and statistical homogeneity. We are not floating in an unstructured void, nor are we embedded in an infinite fractal of ever-growing mass concentrations. We inhabit a universe where the largest coherent forms are measurable, finite, and shaped by balance. The Great Attractor once suggested a hidden gravitational giant. The cosmic web revealed an interconnected architecture. The limits of structure show that this architecture has edges, not sharp physical walls, but mathematical boundaries. Understanding those edges is not a disappointment. It is clarity, and clarity is what transforms mystery into comprehension. At first, the idea of the larger structure invites a kind of competition. What is bigger than the Great Attractor? What surpasses the Sloan Great Wall? Is there something spanning half the observable universe? But cosmology is not a contest of scale. Every time we identify a vast formation, its existence ultimately traces back to the same small set of principles. Gravity acting on dark matter seeded by minute fluctuations in the early universe, evolving within an expanding space increasingly dominated by dark energy. The universe does not escalate endlessly. It expresses its laws across different scales, from planetary systems to galaxies to filaments, and then it stops where those laws require it to stop. The largest meaningful structure is therefore not defined by an extreme outlier. It is defined by the intersection of physical limits. The homogeneity scale marks where clustering fades statistically. The turnaround radius marks where gravity loses to expansion. The cosmic horizon marks where observation ends. Beyond those thresholds, the question changes from how large can structure be to what does structure even mean? Because coherence, true physical unity, requires gravitational binding and causal connection, and those have limits. The grandeur of the universe is not in boundless accumulation. It is in the consistency with which simple rules shape immense complexity. Which brings us to the final reflection. We began with a galaxy in motion. The Great Attractor revealed that even the Milky Way is not still. That realization expanded our perspective outward to superclusters, to the cosmic web, to immense walls of galaxies stretching across hundreds of millions of light years. Then the question shifted. If structures can be that vast, how far can the hierarchy extend? The answer is not infinite. The universe can build filaments spanning hundreds of millions of light years. It can assemble superclusters approaching 1 billion light years in extent. It can weave patterns that fill the observable cosmos with intricate geometry, but it cannot build without boundary. Gravity is limited by the amplitude of primordial fluctuations. Dark matter amplifies structure, but only from these initial seeds. Dark energy halts further growth. Homogeneity restores statistical balance beyond a certain scale. The cosmic horizon confines what we can ever detect. Together, these constraints define the maximum scale of meaningful structure. The largest structure the universe can build is not an endless wall stretching forever. It is the cosmic web itself at its peak during this specific epoch of cosmic history. And that web is temporary. In the distant future, it will thin, fragment, and fade beyond view, leaving behind gravitational islands in expanding darkness. So the search for the larger structure does not end with a record-breaking measurement. It ends with an understanding. The universe is vast, perhaps infinite in extent, but its architecture is finite, evolving, and governed by balance. Grandeur is not measured by infinity. It is measured by how far simple laws can shape matter before the expansion of space sets the final limit. And within those limits, the cosmos has built something extraordinary. When we ask how large the universe can build, we are really asking how far its laws can stretch. The answer is not written in a single number, it is written in relationships. Between gravity and expansion, between dark matter and dark energy, between the tiny fluctuations of the early universe and the vast web we see today, the largest structures are not accidents of scale. They are the natural consequence of those relationships playing out over billions of years. If the initial fluctuations had been slightly weaker, structure would be smaller and more diffuse. If dark energy had dominated earlier, superclusters might never have formed. If gravity was stronger, collapse could have erased large-scale patterns entirely. Instead, we inhabit a universe balanced at just the right moment to reveal its architecture at near maximum clarity. That does not make us central, it makes us fortunate observers. The Great Attractor taught us that we are moving through a gravitational landscape. The cosmic web showed us the geometry of that landscape. The limits of structure show us where that geometry ends, and in understanding that boundary we see something deeper. The universe is not an unbounded accumulation of mass. It is a system governed by coherence where even its largest forms are shape-constrained and ultimately temporary, which leaves one final thought to carry forward. At the beginning, the question seemed almost dramatic. Is something enormous pulling our galaxy? Is there a structure so vast it reshapes the cosmos? The answer turned out to be both simpler and more profound. Yes, our galaxy moves within a gravitational landscape shaped by immense structures. Yes, the universe builds patterns of staggering scale. But no, those structures are not limitless. They are not infinite towers of matter stretching beyond physics. They are the largest coherent forms allowed by the universe's initial conditions and its accelerating expansion. The Great Attractor was not a cosmic monster. The largest walls are not eternal fortresses. The web itself is not permanent architecture. They are expressions of balance. Gravity gathers. Expansion disperses, dark matter scaffolds, dark energy restrains. From those interactions, structure emerges, reaches its peak, and slowly yields to isolation. The largest structure the universe can build is therefore not defined by excess, it is defined by equilibrium. And perhaps that is the most elegant conclusion of all. The cosmos is not chaotic accumulation nor infinite collapse. It is a system where even the grandest patterns obey boundaries, where scale is vast but never without limit. And within those limits, galaxies drift, filaments stretch. And for a brief cosmic moment, the architecture of the universe is visible to us. There was a time when structures like the Great Attractor lived only in inference hinted at through motion, hidden behind dust reconstructed from subtle temperature differences in ancient radiation. Today we map galaxies by the millions. We trace dark matter through gravitational lensing. We simulate billions of years of evolution inside supercomputers. What once sounded mysterious now fits inside a coherent framework, and yet the scale remains astonishing. Filaments hundreds of millions of light years long, clusters weighing quadrillions of suns, a web spanning the observable universe. The difference is not that the universe became smaller, it is that it became measurable. We no longer ask whether something supernatural pulls our galaxy. We calculate velocity fields, we measure turnaround ready, we test homogeneity statistically, we quantify the influence of dark energy. The grandeur remains, but it is anchored in physics. The largest structure the universe can build is not an object to be feared or mythologized. It is a consequence, the natural outcome of simple laws applied over immense time, and that realization transforms awe into understanding. We are not standing at the edge of an unknowable abyss. We are tracing the boundaries of structure with tools forged from reason and observation. The universe is vast beyond intuition, but it is not beyond comprehension. In the end, the question of the largest structure is not about extremes. It is about boundaries. The universe may extend far beyond what we see. It may even be infinite in extent. but structure within it, coherent, gravitationally meaningful structure, is not infinite. There is a maximum scale where clustering remains significant. There is a maximum radius where gravity can resist expansion. There is a maximum domain we can ever observe. Beyond those thresholds, the language of structure begins to dissolve. Filaments become statistical fluctuations. Walls become alignments of probability. Superclusters become temporary features in an evolving landscape. What remains are the principles. Gravity organizes matter locally. Dark matter provides the hidden mass. Dark energy stretches space relentlessly. Initial conditions set the blueprint. From those ingredients, the universe constructs its largest patterns and then it stops. The Great Attractor was never a destination. The cosmic web was never permanent. The largest structure the universe can build is therefore not defined by boundless scale, but by the balance of forces that allow structure to exist at all. And within those limits we find something extraordinary. A cosmos vast enough to inspire awe, and ordered enough to understand. We set out to find the largest structure the universe can build. Along the way, we followed the motion of our galaxy. We traced the hidden mass of the Great Attractor. We mapped superclusters, great walls, and filaments stretching across unimaginable distances. Each discovery seemed to push the boundary outward, but every expansion of scale returned to the same conclusion. There is a limit, not a wall at the edge of space, not a final object beyond which nothing exists. A limit written into the physics of the cosmos. The amplitude of primordial fluctuations sets how much contrast can grow. Gravity gathers matter, but only where density allows. Dark energy halts further large-scale collapse. Homogeneity restores statistical balance beyond a certain scale. The cosmic horizon confines what we can ever know. The universe may be immense beyond comprehension, perhaps infinite in extent, but structure within it is finite, evolving, and temporary. We happen to live at a time when that structure is near its peak, when the web is visible, when superclusters still connect across space, when motion toward attractors can still be measured against the afterglow of the Big Bang. In the distant future, much of this architecture will fade beyond view, but the laws that shaped it will remain. The largest structure the universe can build is not a monument. It is a phase, a moment in cosmic history when gravity and expansion briefly coexist in dynamic balance, allowing matter to assemble into patterns vast enough to move galaxies, yet bounded enough to remain coherent. And within that balance we find the true scale of the cosmos, not infinite accumulation, but structured grandeur precisely as large as physics permits. Gravity gathered matter into stars. Stars assembled into galaxies. Galaxies wove themselves into a vast cosmic web stretching across unimaginable distances. We mapped the Great Attractor. We traced the larger structures the cosmos can create. We discovered that even these immense formations are temporary. But what happens when the building stops? When expansion outruns gravity? When superclusters drift beyond reach? When the web itself begins to thin and disappear? What will the universe look like after the last structure fades? Tonight we follow the cosmos beyond its peak into a future where galaxies fall silent, light grows rare, and the architecture of the universe dissolves into darkness. For nearly 14 billion years the universe has been an engine of construction. Hydrogen collapsed into the first stars. Stars forged heavier elements. Galaxies assembled through mergers. Filaments stretched across space, connecting clusters into a cosmic web. For a long time, gravity dominated this process. Structure grew steadily. The universe became more complex with time. But that growth is not endless. Observations of distant supernovae reveal that cosmic expansion is accelerating. Dark energy now outweighs matter in shaping the large-scale behavior of the universe. The balance that once favored collapse has shifted towards separation. We are living near the peak of cosmic structure formation. Galaxy mergers still occur. Star formation continues, though, at a slower rate than in the past. Superclusters remain visible across hundreds of millions of light years. The web is intact, Yet the trend is clear. Star formation has already declined dramatically from its maximum roughly 10 billion years ago. The rate at which new galaxies assemble has slowed. Expansion increasingly stretches space faster than gravity can compensate. The universe is not collapsing, it is thinning. The Great Architecture we have mapped attractors, walls, filaments represents a temporary high point in cosmic organization. From here forward, the dominant process is not assembly, it is isolation. As dark energy continues to accelerate expansion, something subtle but irreversible begins to happen. Galaxies that are not gravitationally bound to us move away faster and faster. Their light stretches to longer wavelengths. Their brightness fades. Eventually, their recession speed exceeds the speed at which light can bridge the expanding space between us. They cross the cosmic event horizon. This does not mean they disappear instantly. It means that any light they emit after that point will never reach us. Over time, more and more galaxies slip beyond causal contact. From our vantage point, the universe will appear to shrink. Not because space contracts, but because distant structures become observationally inaccessible. Superclusters that once filled our sky will fade into darkness. The cosmic microwave background will redshift to wavelengths so long that even advanced civilizations may struggle to detect it. Evidence of cosmic expansion itself could become impossible to measure. Eventually, only galaxies gravitationally bound to the local group will remain visible. In roughly 4 to 5 billion years, the Milky Way and Andromeda will merge. Other nearby dwarf galaxies will join the combined system. The result will be a single massive elliptical galaxy surrounded by a halo of dark matter, isolated in expanding space. This is the beginning of the era of island universes. The vast cosmic web we see today will not be erased physically, but it will be erased from view. After enough time has passed, the universe will look profoundly different from the one we see today. All galaxies not gravitationally bound to our merged remnant will have slipped beyond the horizon. The intricate lattice of filaments and clusters, once stretching across hundreds of millions of light years, will no longer be visible from within our local region. The cosmos will appear small. Observers inside the future merged galaxy might see only a single vast stellar system surrounded by darkness. No distant galaxies, no cosmic microwave background, no clear evidence of expansion. From their perspective, the universe could seem static and finite. The term island universe, once used in the early 20th century to describe galaxies before their true nature was understood, will regain a literal meaning. Each gravitationally bound cluster will become an isolated island in an ocean of accelerating space. Structure will not vanish everywhere at once. It will fragment, clusters remain intact, groups remain bound, but the connections between them, the filaments that once defined the web, become causally irrelevant. Expansion stretches them into invisibility. This isolation is not destruction, it is disconnection. The universe does not collapse into chaos, it drifts into separation, and as galaxies withdraw from one another, another transformation begins not in space but in the stars themselves. Even before galaxies disappear beyond the horizon, another process is already underway. Star formation is slowing. The universe reached its peak rate of star birth roughly 10 billion years ago. Since then, the supply of cold molecular gas, the raw material for new stars, has steadily declined. Galaxies have used much of their available fuel. Interactions and mergers trigger bursts of formation, but the overall trend is downward. In the distant future, this decline continues. Massive stars burn quickly and die violently as supernovae. Medium-sized stars like our Sun exhaust their hydrogen and shed their outer layers, leaving behind white dwarfs. Only the smallest stars, red dwarfs, endure for trillions of years, burning their fuel slowly and steadily. Eventually, no new stars will form at all. Galaxies will become collections of aging stellar remnants. White dwarfs, neutron stars, black holes, and long-lived red dwarfs gradually exhausting their hydrogen. The night sky within an island universe will dim. It will not go dark immediately. Red dwarfs can shine for trillions of years, far longer than the current age of the universe, but the brilliant blue stars that once illuminated spiral arms will be gone. The vibrant regions of active star formation will fade. The universe will enter a quieter era, not violent, not explosive, just steadily dimming. And when the last red dwarfs finally burn out, the cosmos will pass into an even more extreme phase, one dominated not by stars, but by their remnants. Trillions of years from now, the final generation of red dwarf stars will approach the end of their long lives. Unlike massive stars, they do not explode. They simply exhaust their hydrogen, slowly shrinking and cooling until fusion ceases. The universe will enter what cosmologists call the degenerate era. By this time, galaxies will consist primarily of stellar remnants. White dwarfs, dense cores of once sun-like stars, will cool, gradually radiating away their residual heat over immense timescales. Neutron stars, even denser, will spin down and fade. Black holes will quietly dominate the mass of galaxies, their gravitational influence shaping the motions of surrounding remnants. There will be no new light born from nuclear fusion. The cosmos will not be empty, but it will be quiet. Gravitational interactions between stellar remnants will continue. Occasionally, collisions between white dwarfs may produce brief flashes of light. Black holes may merge, releasing gravitational waves, but these events will be rare compared to the vibrant star-forming epochs of the past. Over quadrillions of years, even white dwarfs will cool to near absolute zero, becoming dark, inert objects, sometimes called black dwarfs. Neutron stars will grow colder still. What remains is matter without shine. Structure persists but without illumination. And eventually, even the most massive objects in the universe will face their own slow transformation. Because black holes too are not eternal. Black holes will become the dominant gravitational anchors of the late universe. Over unimaginable stretches of time, stellar remnants will interact gravitationally. Some will be ejected from galaxies, others will spiral inward towards central black holes. Through rare but inevitable encounters, black holes will merge, forming ever more massive singularities at the hearts of isolated island universes. This era will last far longer than the age of stars. But even black holes are not truly permanent. In the 1970s, Stephen Hawking demonstrated that black holes are not completely black. Quantum effects near the event horizon allow them to emit extremely faint radiation, now known as Hawking radiation. This process causes black holes to lose mass very slowly. For stellar mass black holes, the evaporation timescale is on the order of 10 to the power of 67 years. For supermassive black holes, it is vastly longer, perhaps 10 to the power of 100 years or more. These numbers exceed any intuitive grasp. Yet over such timescales, even the largest black holes will gradually evaporate. Their mass will convert into low-energy radiation, dispersing into an ever-expanding universe. During this black hole era, structure still exists in a minimal sense. Isolated gravitational wells slowly dissolving. Eventually, however, even those wells will disappear. What remains afterward is not a web, not a galaxy, not even a star. It is a universe of extreme sparsity. And in that final stage, the question of structure changes once more. When the final black holes evaporate, the universe enters its most desolate phase. No stars, no galaxies, no gravitational anchors binding matter into coherent systems. What remains are particles, electrons, positrons, perhaps stable remnants of dark matter, and an ever-thinning bath of low-energy radiation. Space continues to expand, driven by dark energy, stretching what little remains farther apart. Temperatures approach absolute zero. There are no luminous objects left to illuminate space. No nuclear fusion, no accretion disks, no supernovae. Only rare particle interactions occurring across distances so vast that even those interactions become improbable. This is sometimes described as the heat death of the universe. Not an explosion, not a collapse, but a gradual leveling. Energy becomes evenly distributed. No region holds enough concentration to perform work. Without gradients, no large-scale processes can occur. Structure in any meaningful sense has dissolved completely. The cosmic web is gone. Superclusters are gone. Black holes are gone. What remains is expansion and entropy. The universe does not end with violence. It fades into equilibrium. And in that equilibrium, the question of the larger structure loses its meaning entirely. Faced with this future, a natural question arises. Is this truly the end? Some speculative models have proposed alternatives. Cyclic universes, quantum fluctuations giving birth to new regions of space-time or vacuum decay events, triggering new phases of cosmic evolution. But under the currently favoured cosmological model, a universe dominated by dark energy with a constant energy density, there is no large-scale collapse. Expansion continues indefinitely. Quantum fluctuations will still occur, but in a universe so dilute and so cold that the formation of meaningful structure becomes extraordinarily improbable. Random particle interactions might produce transient events, but not organized galaxies or stars. There is no mechanism in the standard model of cosmology that rebuilds the cosmic web after it dissolves. The architecture we observe today is not part of an endless repeating cycle. It is a one-time expression of structure under specific initial conditions. The early universe provided slight density variations. Gravity amplified them. Dark matter scaffolded them. Dark energy eventually halted their growth. Remove any of those ingredients or change their balance and the outcome would be different. But under the physics we observe, once structure disperses beyond recovery, it does not return. The universe does not rebuild. And that realization reframes everything that came before. The Great Attractor, the cosmic web, the largest walls and superclusters. They are not permanent monuments. They are fleeting configurations in a universe with a finite era of structure. When we look back across this arc from the Great Attractor to the final evaporation of black holes, a pattern emerges. The universe has a life cycle of structure. In the beginning, there was near-perfect smoothness. Then came growth gravity, sculpting matter into stars, galaxies, and filaments. Then a peak, the era we inhabit, when structure is mature, interconnected, and still visible across cosmic distances. And finally, decline, expansion, thinning the web stars, fading black holes, evaporating. We are living in the brightest and most structured phase the universe will ever have. There were no galaxies in the early universe. There will be no galaxies in the far future. Only during this narrow cosmological window do superclusters span hundreds of millions of light years. Does the cosmic microwave background still glow faintly in the sky? And do large-scale flows like those toward the Great Attractor remain measurable? This is not a philosophical claim. It is a physical one. Structure has a temporal peak. We exist within it. The largest structures the universe can build are visible now, not because we are central, but because we are timely, and that makes the present epoch scientifically extraordinary. Which brings us to the final reflection of this entire series. We began with motion, our galaxy drifting toward a region once called the Great Attractor. That simple observation opened a path outward into superclusters, into the cosmic web, into the question of how large structure can become. We discovered that structure has limits, not because the universe lacks scale, it is vast beyond intuition, but because its laws impose boundaries. Gravity gathers matter, but only from seeds written to the early universe. Dark energy stretches space, eventually halting further growth. The cosmic horizon restricts what we can observe, and over immense spans of time, even the grandest architecture dissolves. The web thins, galaxies isolate, stars fade, black holes evaporate, entropy levels all gradients. The largest structures the universe can build are not eternal monuments. They are phases. We live during the peak of cosmic organization, when galaxies still connect across filaments, when superclusters still influence motion, when the afterglow of the Big Bang still whispers through space. That phase will end, but its existence reveals something profound. The universe is not static. It is not infinitely building. it is not endlessly collapsing. It evolves from simplicity to complexity, from smoothness to structure, from brilliance to quiet equilibrium. The Great Attractor was never just about what pulls our galaxy. It was the first hint that we inhabit a cosmos in motion. A cosmos that builds peaks and eventually lets go. And in understanding that arc, we do not shrink the universe. We see it clearly. There is one final perspective to hold on to. Everything we have traced the motion of galaxies, the limits of structure. The fading of stars unfolds over timescales so immense that they dwarf human history into invisibility. And yet here we are, on a small planet orbiting an ordinary star inside a galaxy, moving along a filament of the cosmic web during the brief epoch when structure is both mature and still observable. 14 billion years after the beginning, the universe has reached a state where its architecture can be mapped, its motion measured, its future projected. Too early and structure would not yet exist. Too late and evidence of it would be gone. We exist at a time when the cosmic web is visible, when superclusters still connect, when the afterglow of the Big Bang still fills the sky, and when the laws shaping everything can be tested. The larger structures the universe can build are not permanent, but they are knowable right now. The Great Attractor is not pulling us toward a final destination. The cosmic web is not an eternal framework. They are features of a universe in motion at a particular stage of its evolution, and we are observers within that stage. The cosmos will continue long after structure fades, but this moment when galaxies still drift through filaments and the architecture of the universe is written across the sky belongs to us.